Okay, guys, so here is the classwork for day two, the week 329 to 41, day two. So yesterday you were looking at, you did an exam or a quiz, and then you watched the Bill Nye video on motion. So hopefully that gave you a preview of what we're going to talk about today, which is Newton's three laws of motion. And then once you're done watching this video, you can complete the worksheet for INL. If you need more review on Newton's three laws, I also included links to two other videos which go over Newton's three laws of motion. So feel free to watch those as well, but you don't necessarily have to watch those videos. Okay, just make sure you complete this worksheet. And the worksheet asks you to pick or to go through these different scenarios and tell me which rule basically is being followed in each scenario or described in each scenario, and tell me how you know that. So you're answering these questions. So answer the following questions, then state if the question is an example of first, second, or third law of motion, and explain how you know that. Okay? So today we're going to talk briefly about the three laws of motion. So the three laws of motion are listed here. Law number one is the law of inertia. An object at rest stays at rest, and an object in motion stays in motion, unless acted upon by an outside force. Okay, and a force is simply a push or pull. Law number two, I often call it the football rule because it is very indicative of what football kind of the principles behind football. Force equals mass times acceleration. So the acceleration of an object depends on the mass of an object and the amount of force applied. And we're going to talk about how force is measured in newtons. We'll also talk about the difference between mass and weight. Okay, law number three is the golden rule. And the golden rule here is that for every action, there is an equal and opposite reaction. Okay, forces act in pairs. So you have an action and reaction pair. Okay, the golden rule in general is treat others how you like to be treated, because whatever you give out, you're going to get back. Same thing here. Okay, whatever action a object takes, it's going to get the same force in return. Okay, then we'll talk about a little bit about momentum, and momentum is often it's abbreviated with a P. It's actually a different, I don't remember what Greek letter it is, but it looks like a P, and it equals mass times velocity. And momentum is basically a property of an object that depends on an object's mass and velocity. Okay, so first one, again, the law of inertia. Object at rest stays at rest, object in motion stays in motion. Okay, and a force is a push or pull. So first of all, forces, push or pull. We can talk about contact forces, so forces that are where two things are in contact with one another. So applied force, spring force, drag force. Drag force is from air on it. And then frictional force, so friction, like if you're moving something across the floor, there's friction across the floor. And then the normal force. The normal force is the force created by the perpendicular to an object. Okay, so the force perpendicular to the floor and the object. It's perpendicular. All right, and then there's no contact forces like magnetic force, electrical force, and gravitational forces. These things you don't need to be touching to experience these forces. The two objects don't need to be touching. Okay, so we talk about inertia. Inertia is actually a property of matter, and it describes an object's resistance to change in motion. So a good example of this is that a car has lots and lots of inertia compared to a bicycle. Okay, a car has a lot of mass. It is very hard to move a car. It takes a lot more force to move a car than it would to move a bicycle. Okay, so an object's inertia is really dependent on its mass as well as its acceleration. If something's moving fast, or its velocity, if it's moving fast, it's going to be harder to slow down. Okay, now if you think about it, um, an object at rest stays at rest, and an object in motion stays in motion unless acted upon an outside force. So why, if you roll a ball on the ground, does it eventually stop? Well, if you roll a ball on the ground, uh, the force that's acting upon it is actually the friction from the ground. So not only is gravity acting upon it, so gravity is pushing it down towards the ground, but then there's also friction slowing the ball down. If we remove gravity and we remove friction, so if we take the ball and we throw it in space, so there's no friction, there's no air molecules, and there's no gravity pulling it, there's no forces interacting, that ball will move in that same direction forever. Okay, so it'll keep moving in that direction until it encounters another force that will either slow it up or speed it up. Okay, so think of inertia in terms of outer space, right? If an object isn't moving in space, if it's moving in space, it's going to keep moving in that direction until acted upon by an outside force. Okay, on Earth, there's lots of forces that are interacting. There's air resistance, okay, or drag force. There's frictional force, the frictional force of the ground, or whatever object it's on. And then there's gravity as well. There's gravity. So all sorts of forces are acting upon objects on Earth. Okay, so we don't really get to see, when we look at inertia on Earth, it's a little bit tricky to understand. Okay. Now when we talk about inertia, we can talk about this idea of mass and weight. Okay, mass is how much matter an object contains. Mass is a constant for any body. It doesn't change with location. And the unit for mass is generally kilograms. If you're on the Earth, your weight and your mass, your mass will always be the same. However, your weight will change dependent on location. Okay, so if you're on Earth, your weight is greater than it would be on the moon, but the mass would always be the same. So weight is actually a measure of force. Weight is actually the force exerted on mass by gravity. Okay, so weight isn't really a constant. We're going to talk about mass versus weight a little bit later when we talk about projectile motion. We talk about gravity. So free fall and all that good stuff. We'll be talking about weight versus mass a little bit more. Weight changes as we change the force. Okay, and usually we measure weight actually in newtons. Okay, sometimes you'll see, actually on Earth, our mass and our weight are the same. But as we change locations, our mass and weight change. So we can take our weight in units of kilograms or pounds, okay, on the Earth. But if we take it somewhere else, we want to find the mass of an object on the moon, we can't just measure the weight and say it's the same, because it's not. Okay. If you want to weigh something in a spaceship, so if you're in orbit, if you're in space, there's no gravity, right? So if you want to weigh something in space, you want to find its mass or its weight, you basically have to spin it. You have to change its acceleration, or you have to spin it, and then you can tell the force, or the centripetal force, or the force of it pulling, and you can actually weigh it that way. That's kind of how the astronauts weigh themselves on the space station. It's also how they weigh objects that they pick up from the moon, or because when astronauts go to the moon to gather rocks, they can only carry a certain mass of rocks. Okay, so they have to be able to weigh them, or find their mass. If they try and carry too much, the ship won't take off. It won't reach Earth. So they have to be careful. They have to be able to weigh them, so they can weigh them on the space station. Okay. Law number 2 is the football rule. The football rule is simply that the acceleration of an object depends on the mass of the object and the amount of force applied. Okay, if you want to move something faster, you either need more force or less mass. Okay, the more mass you have, the more acceleration you have, the more force you're going to need. So you think about a football player is really big. It doesn't really have to move that fast to create a lot of force. So you have those big offensive linemen that weigh like 350, 400 pounds. Those guys really don't have to move that much. They kind of just stand there. Whereas if you have a running back that maybe weighs 200 pounds, they got to hit those they got to hit those linemen really, really fast to break through that line. Okay, to move them, to get them accelerating backwards. Okay? That's why I think about the football rule. Okay? If you think about a bullet has a lot of force. The reason it has a lot of force is because its acceleration is very great. Its mass is really small, but its acceleration is very great. Okay, so if to have a lot of force, you either need a lot of mass or a lot of acceleration or a little bit of both. Law number 3 is the golden rule. So for every action, there is an equal and opposite reaction. Right? This is also the idea that forces act in pairs. So if a cue ball hits another ball, okay, this cue ball hits the other ball and pushes it in the opposite direction. Right? So the amount of force that this cue ball hits the other ball with is actually going to be conserved, and you'll have just as much force between the cue ball and the other ball in the end, but they transfer forces. Okay, so the cue ball is transferring its force to the other ball. So the golden rule here is treat others how you'd like to be treated. So whatever you give, you get in return. Okay, and we have action-reaction pairs. And again, we'll kind of be talking about all these things a little bit more. This is just kind of an introduction to it and give some examples. Then we'll be talking about each one kind of here and there. All right. Now, momentum is very similar. It's very similar to force, except in this case, momentum is just mass times velocity. So we're not changing the speed here. The speed is just staying constant because remember, acceleration is a change in speed. Okay, so we have mass times velocity is momentum. So the more mass you have and the faster it's going, the more momentum you have. Okay, so let's look at these examples here. So you can pause for a second after I read it and then think about it and then see if you come up with the right answer. So a soccer ball is motionless on the field until a player comes and kicks it. So think about that. Okay, so here we have a soccer ball that's motionless, so it's staying in place until the player comes and kicks it. So until an action occurs. So this would be law number 1, the law of inertia. The soccer ball will remain at rest until something comes and changes that. Okay, so this is Newton's law number 1, law of inertia. So the ball is staying in place until something comes and kicks it and moves it. So that's number 1. Example number 2. Think about this one. A rocket is moving through space at 500 kilometers per hour towards the moon without any of its boosters firing. So this one, the speed, the motion is staying constant, so motion is not changing. But we don't have any forces acting upon it. So the boosters aren't firing, there's no air friction, there's no gravity. So basically, this object is in motion, so it will stay in motion until something comes along and acts upon it. So right now, this is Newton's first law again, Newton's first law of inertia. Example number 3. The air is released from a balloon and it flies all over the place. So if you take a balloon, you release the air. What is going on there? This one is actually Newton's third law. Newton's third law. You could probably explain how Newton's second law applies here as well, but really this one's showing for every action, there's an equal and opposite reaction. So as the air is released, as the air is pushing out from the balloon flies all over the place. This is every action has an equal and opposite reaction. The air is being blown out and the balloon is flying all over the place. Okay, number 4. You jump off a small rowboat and the boat moves backwards. You're going on a boat and you're going to jump in the water. As you jump, the boat moves backwards. So this one is Newton's third law again as well. For every action, there's an equal and opposite reaction. So you jumping off the boat, you're pushing off the boat, jumping in the water. The boat moves backwards and you move forward. Okay, the boat moves backwards, you move forward. That's the action-reaction pair. You're moving forward, that's the action. The boat moves backwards, that's the reaction. Action-reaction pair there. Next one, a mail carrier finds it much easier to push his mail cart at the end of his shift when all of his packages are delivered. The mail carrier is pushing his cart and he's delivering his mail, and as he goes, it becomes much, much easier to move. So basically, the force required to move the move the cart is getting less and less because the mass is becoming less and less. So this is Newton's second law, that force equals mass times acceleration. So as you decrease the mass, you need less force to accelerate it. The last one, two football players run into each other at full speed. The smaller player is pushed backwards by the larger player. So if both players are running at the same speed or somewhat relative speed, the one who has less mass is going to create less force. Therefore, he's going to be pushed backwards by the larger player. Okay, so this is the second law again. Force equals mass times acceleration. Okay, feel free to watch. That's the last example here. Feel free to watch the other videos that I've included, as well as any other videos online that you think might help. And good luck with the worksheet.